In this video, we'll talk about the normal equations. This will give us a much more efficient way to implement the least squares learning algorithm. To put this in context, so far we've been talking about using gradient descent to minimize our cost function j of theta. And so we have our cost function, and then using gradient descent, we will start somewhere, and then we'll take a bunch of steps to get down to the global optimum. But it turns out that we can solve for the parameter theta analytically without needing to use an iterative algorithm like gradient descent. The intuition is as follows. Suppose j of theta is a function like this. So in this intuition, I'm going to use a example where theta is just a real number. So if theta is a quadratic function, like so, say, if theta were just a real number rather than a vector, right? Then if you wanted to minimize theta, if you wanted to minimize j of theta as a function of theta, well, one thing you can do, one way to minimize a function like this is to take derivatives, set the derivative equal to 0 and solve, and that will let you find the minimum, right? So what you do is you take the derivative of j of theta with respect to theta, you set the derivative equal to 0, and then solve for theta. And if you can do this, which you can't do in closed form for all values of theta, but you can for a quadratic function like this, say, then you'd be able to find the minimum right away. In our setting, j of theta is a function of theta 0, theta 1, theta 2, up to theta n, if you have n features. And we had defined j of theta as follows, right? It was this sort of quadratic cost function. And so what we're going to do is take the partial derivative of j of theta with respect to each of our parameters. So we're going to do this for every j equals 0 up to n. And then we're going to take, figure out what this partial derivative term is and set it equal to 0, and then use this to solve for theta. Okay? So this is the conceptual explanation of of how we're going to find analytically find in closed form the minimum of j of theta. This is how you would actually go about deriving it. But in practice, I guess this derivation is extremely involved, and I'm not going to do that mathematical derivation here, which requires some amount of calculus and fair amount of linear algebra. And what I'm going to do is instead just tell you how to compute the value of theta that you would get from doing this process, and I won't actually go through this derivative and so on derivation in this video. Okay. So how do you compute theta in closed form? Well, we have m training examples, right? We have x1, y1 up to xm, ym. In order to, and we have n features, right? And so, xi is going to be a vector, x0, I, x1, I, and so on down to xni. And this is going to be an n plus 1 dimensional vector. And the plus 1 is because we have this extra, right, x0 feature, which is always equal to 1. So the first thing I'm going to do is I'm going to compute a matrix, which I'm going to write as capital X. And the way I construct this matrix is I'm going to take each of my training examples, x1, x2, and so on, down to xm. And I'm going to stack them in rows to form this matrix X. So technically, this is going to be x1 transpose, x2 transpose, up to xm transpose. Okay, and it turns out this will be an m by n plus 1 dimensional matrix because I have m training examples, so m rows, and each row is going to be one of my training examples, which is n plus 1 dimensional. So just be clear, suppose you have only one feature x1, right? Or suppose n equals 1. then each of your training examples will be two-dimensional. So xi will be equal to, x0, I, x1, I, and the first feature is always equal to 1, so it's going to look like 1, x1, I. And if I take my training examples and stack them in rows, then my matrix X is going to be, this first row is going to be x1 transpose, and so there's going to be a 1 here, and an x1, 1. The second row is going to be x2 transpose, I have a 1, x2, 1, and so on, down to 1, xm, my last training example, 1. And so this is my matrix X. And X, by the way, is sometimes called the design matrix, but I'm not going to worry too much about what it's called. Second thing I'm going to define is a vector Y. So the way I'm going to construct my vector Y is I'm just going to take all the labels in my training set, Y1, Y2, down to Ym, and just stack them in a big vector. So this is going to be an m-dimensional vector. That's just, sometimes I'll draw an arrow over Y just to denote that that's a vector. And with this definition of that X, my training example stacked in rows, and of this vector Y, my labels stacked into a matrix, stacked into a vector, what I'm going to do is just compute theta as X transpose X inverse X transpose Y. And it turns out this is the analytic closed form solution to the problem of how to minimize as a function of theta, j of theta. Okay, and this turns out to give you the optimal value of theta. Obviously, I didn't do any of the derivation. I'm just claiming that if you implement this procedure, you get the global minimum of j of theta. This actually works, but you don't have to take my word for it. And in the next exercise, you get to implement this yourself and verify for yourself that you get the same answer using this formula as you do for gradient descent. Just a couple notes on maybe the notation, this thing here, X transpose X inverse. So X transpose X inverse is the inverse of the matrix X transpose X. And in case you don't remember what matrix inverses are, right? If you have a matrix A, then A inverse is the matrix. A inverse is the inverse of the matrix A, and it has the same dimension as the matrix A. So if A is a, n by n square matrix, A inverse will have the same dimensions. And the inverse of a matrix satisfies that A inverse A is equal to the identity matrix, and A times A inverse is also equal to the identity matrix. And concretely, the way you would implement this in MATLAB or in Octave is you would write, INV of x prime times x, where as before x prime, that is in MATLAB and Octave, that's how you implement x transpose, and INV is the function that computes the inverse of a matrix. Finally, one thing I want to address is what if X transpose X is not invertible, right? So let me just write that down again. Theta equals X transpose X inverse times X transpose Y. And it turns out that some matrices are not invertible. So there exist some matrices for which there is no inverse. So what if X transpose X is non-invertible? Non-invertible. And a synonym for that is a non-invertible matrix we also call a singular matrix. So as an example, if you have a 1 by 1 matrix, right? If you have a 1 by 1 matrix, that's just the number 0, right? So this is a 1 by 1 matrix, then that's an example of a non-invertible matrix because, well, you can't invert 0, right? This is not valid. So what if X transpose X, what if you call inv on X transpose X, and this turns out to be a singular matrix or a non-invertible matrix? It turns out that there are two possible causes for this. One is if you have too many features. For example, if the size of the training set m is smaller than or equal to the number of features n. So it turns out that if you have a lot of features in a relatively small training set, then that matrix will be non-invertible. And there are a couple ways to deal with this. One is to use regularization, which is something we haven't talked about, but that we will in a later video, regularization. And this is a way to help deal with if you have a lot of features relative to the size of the training set. Or, and we'll talk about this in a later video, or you can delete some features, right? So, so that's one cause, if m is less than or equal to n. A second cause of this being non-invertible is if you have redundant features. And formally, redundant features, by that what I mean is if you have linearly dependent features. And as a concrete example, let's say x1 is the size of your house in square feet, and suppose x2 is the size of your house in square meters. And so let's see, 1 meter is what? Is it equals or approximately equals to 3.28 square feet? Oh, excuse me, 1 meter is what, about 3.28 feet. And so x1 will be equal to 3.28 squared times x2, right? And so these two features are highly redundant. The technical term is actually that they're linearly dependent, but it's just you really don't need to have one feature to capture the size in square feet and then second feature to capture the size in square meters. And so you really don't need to include both. And it turns out that if you have this set of redundant features, then the matrix X transpose X will be non-invertible as well. And in particular, what you can do is maybe get rid of one of these two features since you really don't need both. And that will take care of the non-invertibility problem of X transpose X as well. So to wrap up, this part, if X transpose X is singular, or equivalently if it's non-invertible, first, think about whether you have redundant features. Or what I was calling linearly dependent features, such as the size in square feet and the size in square meters, because this will cause X transpose X to be singular. And if so, get rid of some. Get rid of the redundancy. Okay? Otherwise, think about whether you have too many features still. Think about whether you have too many features. So that maybe m ends up less than or equal to n. And if you really want them all, and in particular, if you really don't need all these features, maybe you can get rid of some features and make X transpose X non-singular as well. And finally, if you do want so many features, then try using regularization, which we haven't talked about, but we'll do so later, and that will also help get rid of this non-invertible problem, non-invertibility problem. One last thing about using the normal equations. So when using the normal equations, which is the normal equations is the name of the method that we're using to solve for this, right? X transpose X inverse X transpose Y. Technically, the normal equations is a slightly different, slightly rewritten form of this, but when you're using this method, which I'm going to call the normal equations, when you're using the normal equations to solve for theta, you don't need to worry about the scale of theta. And in particular, it's perfectly fine if your first feature x1, ranges from 1 to 2000, and if your feature x2 ranges from 1 to 4, like we saw in our earlier examples, if your features have such different ranges, it would make gradient descent slow, but using the normal equations, this works just fine, and you don't actually need to rescale the features in order to make this algorithm work well. So that concludes our discussion on the normal equations, and hopefully you can take this and use it to get a closed form analytical solution to your least squares problem. And in case you're wondering why we also have gradient descent and why we didn't just talk about this, it turns out that when we talk about later learning algorithms, specifically logistic regression, which we'll go into next, gradient descent will still be very useful. And it turns out that there are different trade-offs between when you want to use an algorithm like the normal equations and when you want to use something like gradient descent. And this is a topic that we'll address also in a later video.